In this video, I'm going to be demonstrating conversion from Cartesian coordinate systems to cylindrical coordinate system. Before we start, let's look at the Cartesian system. We know we have three components: the x, the y, and z, all of them ranging from negative infinity to infinity. So, drawing our three axes, we have z, x, and y. So we will have three planes: the x plane, the y plane, and the z plane. A point in any coordinate system is referred to as where all the surfaces of these components are intersecting. So for our Cartesian, if I say we have a point over here, that means it's a point where all these surfaces are intersecting. And if I say x is 5 and y and z can be anything, then we would be on the x plane. If you are given y and you are told that x and z can be anything, or if y is any constant, then you are on the y plane. And if you're given the z component value as a constant, but x and y can vary, then you will be on the z plane. So now let's look at the cylindrical coordinate system. So for the cylindrical coordinate system, let's just draw the z, x, and y. We know we have a cylinder with its center at the origin, and it's gonna go all the way up. Okay, yep. Here we have our cylinder. Oops. I am really bad at drawing, so forgive me for that. So we know in cylindrical coordinate systems we have three components: rho, phi, and z. Rho ranges from 0 to infinity, and it is the radius of the cylinder. As you can see on this figure, I'm marking what rho is. All of this is rho. And then we have our phi component, which goes from 0. Oops, what am I doing? Okay, so our phi component, which goes from 0, ranges from 0 to 2 pi. It's going to be an angle, so I forgot to draw this, but we also have an infinite half plane coming out of the z-axis. So our phi would just be this angle which we make with that half infinite plane from our x-axis, and our z component is going to be the same as that in our Cartesian system. And any point, if someone's talking about a point, what they mean is an intersection of all these three surfaces: the cylinder, the half infinite plane, and the z plane. And now let's talk about another important concept: unit vectors. So we know unit vectors are, I'm going to denote it as ace of x, y, z, or whatever I'm going to call it, ace of the component's name as referring to the unit vector. So what is important to remember is that a unit vector always points toward its increasing component's value. So let's suppose I have a point over, let me show that first. Oops. Let me show that first in the XYZ Cartesian coordinate system, and I can demonstrate that later. So we have, if let's suppose we have a point over here. So if the unit vectors for the z component would be towards where the z component is increasing, for the y it would be over here where the y component is increasing, and here for the x where the x component is increasing. Similarly, for the cylindrical coordinate system, if I have a point, let's suppose I have a point over here. If I have a point over here, then no, let's do Let's do, yeah, so we will have our a sub c, the unit vector component, in the increasing z direction, and for phi, if this is phi, it's going to be in the increasing phi direction, I mean rho direction. And for phi, we know phi goes from 0 to 2 pi, and to demonstrate, you can think of it as going inside of the page. A sub phi would be going inside of the page because phi has to go all the way around. I think I would be able to better demonstrate it conceptually and explain it better when I'm working on this problem we have right here. So we have been given a uniform electric field intensity in the s of y direction and magnitude 4. And in the table we have been given three different Cartesian points, and they want us to find these points in cylindrical coordinates and the representation of the electric field intensity with unit vectors in the cylindrical coordinate systems. Okay, I think we can do that. So let's see. So for now, our first point, we have our z, our y. Oh, let's just, because all our z's are zeros and it will be easier for me. So this is our y-axis, this is our x-axis. You can think of z-axis as coming out of this page as the positive z-axis, and going inside the page as the negative z-axis. So our first point is somewhere over here. It's 2 meters, and we see our y component is 0. Energy is 0, so it's going to be on this line. So converting this into our cylindrical coordinate, we know we have a cylinder with center at the origin, and the radius is from that center to that point. So this is our phi component. You can see if I draw out a cylinder, the rho value would be same everywhere, and it would be centered at the origin. That's how cylinders are in the uh, cylindrical coordinate system. So we have this point over here, and its length is going to be the same. Its length is the same as our x component. As you can see, we have no y component, so our rho value is the same as our x value, which is 2 meters. So we can write 2 meters over here. Now for our y, now for our second component, which is phi. So we know phi is going to be our angle x-axis makes with the point. So the point lies on x-axis. That means our angle is just 0, and we can write that down. And our z is going to be the same as in Cartesian, so we can put that down. Now coming for our electric field intensity, we need to determine the unit vector, the direction of the unit vectors. So we know that the unit vectors will point towards the increasing component value. So if the point is over here, for in Cartesian, this is our unit vector in the x direction, this is the unit vector in the y direction, and because z is coming out of the page, you can think of the unit vector in z axis as coming out of this page, because all these unit vectors in any coordinate system will go according to where their components direction is for increasing. So now coming to our cylindrical coordinates unit vectors, we can see that if this is rho over here, if you want to increase rho, you will have to go further out, right? So that's our increasing rho component. So we can see that a of x, our unit vector in the x direction, and our unit vector in the rho direction are in the same direction. So we can write this as s of rho equals to s of phi. Now, even though our angle itself is 0, but if it was increasing, it would go like this, right? So till it goes to 2 pi. But at this specific point, we know it will be in the increasing in the same direction as rows of y. And I think I forgot to mention this, but in each coordinate system, all these components are perpendicular to each other. By perpendicular, I mean they have a 90-degree angle with each other, all of them, the x, y, z's, the rho, phi, z. So we know our phi angle is pointing over here, so we have a sub phi and a sub phi. So we know that our direction for our unit vectors of a sub phi and a of y is equal, so we can write this that our electric field intensity is pointing at the ace of y direction as our cylindrical in the cylindrical coordinate system. Now coming for our second point, let me quickly get rid of this. Let me make a axis again. Okay, so we have, okay, so this is y, this is x. We have a point at -2, so this is our point at -2. So we have no x value, no zero. X is 0 and z is 0. So we know we have a cylinder in the cylindrical coordinate system with its uh, center at the origin. So this the radius is going to be to this point. This is going to be our phi component, which will have the whose length is going to be the same as that of our y component, because we don't have an x component. So in magnitude it's going to be the same. It cannot be negative now 2, because rho is going to be from 0 to infinity, and radius cannot be negative of anything. Radius has to be a positive number. So, and if you can see, if we had a cylinder over here, the radius doesn't change, right? So any either way it's going to be 2. But for our point, oops. Okay, so for our point we have rho is equals to 2. So we can write that down over here. Now for our phi. So phi is going to be from our x to our point, where our point lies. So our point lies over here. We can see the angle that it's making is 3 pi over 2 or 270 degrees. Let's write 3 pi over 2 over here. And that's our phi value, and the z value is going to be the same. Now let's determine our direction for our electric field intensity. So we know over here at this point, we in the Cartesian, we have our unit vector at the increasing x component. So this is the a of x. Y is going to be at the increasing with the y component increase. So this is going to be a of y. And now for our cylindrical, we know that rho is coming over here to this point. So our unit vector for rho is going to be over here, and where rho has the potential to increase, so it's going to be s of y. And oops, why did I write s of y? It's going to be s of rho over here. And now we can look at phi. So we know that phi has to be into the where the unit s of phi, the unit vector for phi would be where phi is increasing. So if y is stopping over here, it would increase if it goes over here. So it's going to be in the same direction as our x component. So from here we can see that our components a of x equals to a of phi, and our a of y component is the exact opposite of a of rho. So we can write our electric field intensity as -4 a of y. Okay. Oh no, we have to write it in terms of cylindrical coordinates. So this is just going to be -4 a of rho. Now let's come to our last point. So we have a -2 and a -2. We are in the third quadrant over here. So we can see that our rho component will be pointing towards this direction over here, and if we make out our cylinder, it will be like this. This line over here represents our rho, which is the radius of the cylinder. And now we want to calculate what its value is, so we can just bring these down. So we know that this over here has the same length as over here, so it's going to be square root of 2 2. So over here we have a right angle triangle. So you can use the Pythagorean theorem to calculate this hypotenuse. So our hypotenuse, which is rho, equals to square root of 2 squared plus root 2 squared, all of this under the root. And our negatives are going to turn to positives. Okay, so we have root of 4, which is just going to be 2. So our row component is 2 meters. Now let's see what our phi component is. So the angle x-axis makes with this row. Now this theta, we know it's going to be in the third quadrant, so it's going to be bigger than pi and less than 3 pi over 2. So to calculate this, we can use this symmetry we made. So we have a right angle triangle, and we know the value for our this section. Let me change colors to show you better. So we know what this is, and we know what this is. We just want to know what this is, so we even know what rho is, so you can in essence use any of the trig functions, but let's use tan inverse because initially we had our x and y components. So tangent over here, so we have over here and over here negative square root of 2 divided by negative square root of 2. So these negatives are going to cancel, and you're going to be given pi over 4. Now this pi over 4 is this angle. Now, but we know we're in the third quadrant, so in phi is from our x-axis to our point. So it's going to be pi over 4 plus pi, which gives us 5 pi over 4. So we can write that down, and then our z component is going to be the same. Now to determine the electric field intensity, let me clean all of this up first so we can have more space to go through this. And okay, so for our unit vector, we know we are in our third quadrant. Here is our point. Okay, and oops. Let me be more tidy. So this is our row. So we know our row unit vector is going to be towards the increasing row direction. So this is our a sub row, and our a sub phi is going to be towards the increasing phi component. So if our phi stop here, the increasing would be towards this direction, right? So we have our a's of phi in this direction, and we are already given an electric field in Cartesian in this a's of y direction. So let's see. Okay, so now we have to figure out what our a's of rho and a's of phi are, because our electric field will have a component in both of them. And as you can see clearly from the picture, let's do this. So this angle over here, we know is 5 pi over 4. So we can say that if I take this and take this down, the angle I am making, wait a second, and this is our ace of x direction, the unit vector pointing in the x direction for our x component. So we know we have this angle of 5 pi over 4, and we wanna find what this we wanna get this value. So you can just use, you can say that the electric field in the row direction is gonna be our hypotenuse, which is this 4 value times cosine of 5 pi over 4 times in the ace of row direction. So this gives us 4 root over 2 negative. So we are left with 2 square root of 2. So that's our electric field in the row direction. And coming to our phi direction, we can see that if we, let's suppose, if this is x, this over here, the phi is going to be negative pi over 4. So we can say 4 cosine Let me just make sure if this will work too. If I set this, then my hypotenuse is over here. So this is my hypotenuse, I can say. So y is this line over here. Then this angle, um, it doesn't, it shows as my hypotenuse is a phi. But I guess phi is just gonna be 4 cosine of phi pi over 4. And we multiply it with the s of phi direction. This gives us 4 times root 2 over root, which is just gonna be negative 2 root 2 in the s of phi direction. So we have our component as negative 2 in the s of rho direction and negative 2 in the s of phi direction. Now let me go back and clean this out a little bit so I can show how we got to this point. Let's see. Now this over here, we know this is our unit vectors in s of y and this is our s of x direction. So we know the angle over here for our rho is just gonna be let's see, this, if this is it, this is 90, if this makes 90, this is just 45 degrees right here, right? So this is just pi over 4. So I can show that, yeah, the hypotenuse, which is our 4 2 cosine of pi over 4, also gives us 4 root 2 over 2. And because we know that we are in the third quadrant, we can put our negative sign here and we would get 2 square root of 2. And similarly, we can do this for the phi component and we will get the same result. Thank you.